Hi everyone. So today I'm gonna be presenting the paper from Google research team that is called General Geospatial Inference with a Population Dynamics Foundation Model. And this was published in late 2024. I think it was by the end of November. So it's still fairly fresh. I'll try to tell you guys how this specific model works, but also geospatial foundation models a little bit in general, and maybe how we can apply them to our activities here. So just as an outline, first I'll give a context on what geo foundation models or GeoFMs are. Then I'll introduce this one, which is the population dynamics one by Google. I'll explain its methodology, some of the tasks that they run and their results, how it compares to other GeoFMs, its strengths and limitations, and then we'll have some takeaways and comments to go with it. So first, just giving the context on GeoFMs, as we know, foundation models are very large and general models that trained on very huge data sets and then adapt to specific tasks, right? Like GPT is for language. So a geo foundation model applies the same concept, but to geospatial data. So it's a foundation model that it's specifically trained on spatial temporal data and designed for spatial reasoning, let's say. So in other words, it will get data from maps and satellite images and sensor readings, mobility data, census data, to create a representation of the locations and regions that we want to know more about. So those representations, they can be used for a very wide range of tasks without having to build a new model from scratch for each task. So the goal is to have a single and very powerful model that will capture the essence of those places, and so that we can have many downstream tasks based on that information. So why do we need geospatial-specific foundation models? Wouldn't a general model be able to do the job? So the thing is that general models, they are not trained or tuned for the geographic reasoning or understanding distances. So for example, if you were to ask ChatGPT to predict 2026 hurricane season in Florida, of course, maybe search for predictions, right? But it wouldn't have that kind of both spatial and temporal understanding to make that prediction itself, right? And geospatial data, it also is unique in the sense that, for example, data points that are in space, they're not independent, right? So one thing about geography law is that things in nearby locations, they tend to be more similar the nearest they are, which is a spatial autocorrelation phenomenon. And also, the data can come at different resolutions and qualities. So you can have data for a city, you can have data for a block, for a neighborhood, for an entire country. And also, traditional machine learning, it would often assume independence and identically distributed data, and that more often than not doesn't hold in geography. So yeah, the geo foundation models, they aim to change that by providing a more general reusable model of a place itself that we can then fine tune and put into other tasks. So yeah, it's more about capturing the spatial context and relationships that general models wouldn't be able to. So the current landscape of geofoundation models, it's a fairly new area, but it's quickly growing, especially in the past year. So we already have like a few different types of GeoFMs. So some of them, they focus on language. So they try to adapt LLMs to understand data that is geotagged. So for example, that has like the coordinates, the shape of the polygon drawn out as like a string to answer geographic questions. Others, they focus more on computer vision, especially ones that are more environmental focused, so Earth observation focused. So they use a lot of satellite image, have like SatMAE, SatClip, GeoClip, those recent efforts that actually have been proven to be quite good for these Earth observation tasks, like for example, predicting deforestation or things like that. We also have GeoFM's, like a combined approach with graphs. So, for example, graphs of places or transportation networks. And this one that I'm going to present, the population dynamics one from Google, it's also a graph-based model that integrates multiple data types about locations, also like multimodal foundation model. So yeah, the multimodal ones, they combine different types and sources of data, so text, images, and structured data to create more holistic models that will cover all aspects of spatial information, not just, for example, the satellite images. So yeah, it's a quickly growing field, and right now people are currently working on developing benchmarks. So that there is a benchmark like GeoBench, Pangea. Google has their own benchmark which they use for this population dynamics model. So yeah, and it's still nothing is too how can I say, like set in stone right now. It's something that's still being very like developed, but yeah, it's growing quick in size as well, like the models. So I think it's something cool to keep track of. So now talking more about the specific model from Google, the population dynamics one. So it is a GeoFM that was developed by the health AI team from Google Research, that they wanted to capture relationships that are a little bit more complex, not only in the environment themselves, but also with humans, so the populations. So the idea is that it creates a graph of locations. So the locations in this sense, they use both postal codes, like zip codes in the United States, as nodes, or the counties. And this is something that they didn't exactly explain, like as a little bit, because Google, they have developed a spatial indexing method, like a geohash, for example, with different precisions. They have the S2 indexing. I don't know why they use something more like arbitrary as postal codes and counties. They don't explain that in the paper. I just suspect that it might be because they have relations with the government to develop this model, so they want something like to be applied on like a governmental scale. But I'm not sure, because I think it would be quite nice to have this more like applied in a spatial indexing with a spatial indexing structure. But anyway, so each location node, which is either the zip code or the county, is then loaded with different types of data. They can be like points of interest, how busy, like with foot traffic, the location is, what people in the area are searching for online on Google search, and other environmental things like weather, temperature, air quality. So all of those are aggregated in those levels to, they say, to ensure privacy. They don't make it that granular, right? Especially the Google search data. So yeah, to try to understand the characteristics and the type of human behavior that happens in that location. So they use a graph neural network, GNN, to learn an embedding of that each location. So with the embedding, the idea is to have like a general purpose representation of the human and environmental dynamics there, without, and it can be used for downstream tasks without it being trained for one specific task. So yeah, it's like a kind of a general purpose geospatial, like social, environmental, socioeconomic model, which I think is a pretty cool idea. Um, so why it can be important, how we can apply, right? So basically, it represents like a new level of generality that you can achieve with geospatial data, and also efficiency, because you can use the same model for many other tasks. So yeah, we can use the embedded as a foundation and then just train lighter weight models on top of that. So it can go from tests, like even from predicting, in this case here, they predict like disease rates to estimating the crop yields of a certain year, or socioeconomic indicators like unemployment. Um, and they with the in the paper, like they show the results. They show it to be like a state of the art like performance. So they benchmarked it on various like different prediction tests against like different, at the time, the current GeoFMs that were most well performing at the time. The results were quite good and interesting for all different types of tasks. So that's something that is very interesting. Um, so also something that's really cool is that it can augment existing models. So the researchers, they also showed that using the location embeddings in other models, like more like a forecasting models, for example, um, they can improve the results by adding that layer of spatial, like geographic understanding. And also, it's nice that Google, they have released in the embeddings and also like some notebooks and simple code to play around with the embeddings and downstream tasks. So it's nice that, for example, as we can try to apply that to our tasks here in a fairly relatively easy way without needing to like go through the paper and implementing it. So going through now more specifically through the methodology they used. So first, about the data inputs that they fed. So first they fed aggregate and anonymize the Google search trends data. So things about whether people are searching for in the area. So it would indicate like interests or concerns or needs. So for example, in this case, it's health AI, right? So like flu symptoms, what people are searching for, like I'm feeling this way. So yeah, it gives a window into like the population's behavior. In that sense, they also have like metrics of like how busy the locations are. So it's data that is derived from Google community mobility reports. I think it's their service. So it's basically when you go on Google Maps and you see like, oh, this area is more crowded now than it was supposed to be for this time. Very active, like, so it's about like foot traffic and car traffic as well. So environmental data, they collect weather and air quality data too. So because of course it can heavily influence the health. So they have, for example, pollution, temperature, like cloud cover, if I remember correctly. And they also have like local characteristics of like the built environment. So with Google Maps data, so they have data on the places and the amenities that are there. So the grocery stores, pharmacies, factories, or hospitals. So yeah, it's about encoding basically the built environment and what's available locally. And all of those, as I mentioned, they're aggregated to the zip code or county level. And some of the data, not all of them, they are also segmented in time, so with like monthly averages. So yeah, and then they construct like a GNN. So the nodes in the GNN with this data, they're either the postal codes or the county in all of the continental US. So yeah, they basically have I think it's 30,000 like postal codes and 3,000 counties. Yeah, each node has those features aggregated as the previous slide. So these nodes are connected first. The edges are first by spatial proximity. So for example, for nodes of the same time, like postal code to postal code, they add an edge if they lie within 100-mile radius of each other. So that way each location is connected to its near neighbors geographically, so we have that sense of neighborhood. And for nodes of different type, like for example, between a county and zip code, they connect them from if these areas overlap. So if the postal code is inside the county, and secondly, they have the relationship like similarity based edges based on data similarity. So they look at the similarity of the aggregated search trends. So if two locations, they have very similar search behavior patterns, they connect them with an edge. So that adds like an interesting layer, because even if two locations is very distant from each other, if the people there are behaving similarly, and they say the people behavior here that they're using the search things as a proxy, then these locations will be connected. So yeah, so like this, like the graph will capture like two different kinds of relationships. There is who is near who, and who behaves like who. So it's an interesting thing that I hadn't seen in other foundation models, getting like that human kind of dimension, even if the things are not places are not near direct neighbors. Even if the people there are similar, like they will be connected. It's pretty cool. So yeah, now on to like how the graph neural network will learn the embeddings, right? So it takes that graph, the locations, and it runs a message passing algorithm. So essentially, each node, it starts with its initial features. Then in each next GNN layer, it will exchange information with its neighbors defined by those edges that I just talked about. So that is repeated over multiple layers so that the information can propagate further out across the network. So yeah, the result after several rounds of that is that each node's representation now encodes not just its own data, right, but also it has the influence of the surrounding ones. So yeah, and then the way they train it, so there's no labeled like response value, like a Y value, like predict, like for example, poverty or unemployment rate during the foundation model training. So it's self-supervised, and the model is learning to represent the graph structure and node features in compressed form without like an explicit supervised task. And they kind of hint in the paper that using standard self-supervised GNN, even though like they don't really detail it, that part. But yeah, the key point is that it's just not trained for one set prediction. It's learning like a general representation of the data in those locations and the relationships. So at the end of the training, then each node has an embedding vector, and this embedding is what it's used as the main output, and that is used for the downstream tasks. So yeah, it's a lot of data, but how the team like was able to run that was that they sample, like they had like simple subgraphs, so they wouldn't have to load all of those thousands of nodes all at once. So yeah, by the end we have like the set of embeddings after like those like subtrees of the graph. So one interesting design choice is that the embeddings are disentangled by data source. So basically, when they construct the final embedding vector for a certain location, they allocate specific dimensions of that vector to each type of input. So for instance, suppose the final embedding is 120 dimensions, and maybe 20 of those dimensions that are reserved for like the maps, like the local information, 20 for search trends, 20 for busy metrics, 20 for weather. And this way, each segment of the embedding carries like a specific kind of theme of information. And they do that to encourage the use of all data sources. By giving each data type its own subvector, it ensures that every source has kind of like a some type of voice in the final representation, right? And also because it's more interpretable and it gives a little bit of more transparency to try to understand the model, even though it's quite complex. But also they highlight that this is like a contribution because of the interpretability. So for example, in this application of health, so if we're predicting like a health outcome, when we see that the weather theme is the more important one, it's carrying a lot of the information in the embedding, like we can conclude that then the weather is an important factor, and like for example, the government can act more on it and allocate resources for that, right? So one thing that is also interesting is that the PDFM model is flexible for us to add like new data sources. Like they mentioned in an experiment where they use like the set clip, which is like a computer vision, like a satellite-based foundation model as an additional input. And yeah, it's fairly, they say it's like seamless, but yeah, it's not incredibly difficult to do that, and there are some gains in performance when you try to associate these different types of models. So that's very interesting as well. So yeah, the tests and that they use to test out the model and then the results. So basically, they have like 4 different types of downstream tests. So first, it's interpolation. So basically, it's about filling in missing data points for the region that you already have data for. So imagine that you have, for example, a very patchy like a health survey data set that has been run in some counties but not the others. So or like all the zip codes but not the others. So like how we can predict the data from all those others that were left. So it kind of like fills in the missing pieces of the puzzle. And then they also ran an extrapolation test. So it's a little bit tougher, right, to extrapolate. So extrapolation, like we train one region and then we try to predict it in a different region entirely. So for example, we train a model on data from like the eastern counties in the U.S. and then try to apply it to the western counties of the U.S. And then when there is no training data, and it tests whether the model is understanding can generalize to that entirely different geography. So they also have the task of super resolution. So by analogy to image super resolution, that is like going like from blurry resolution to sharp. Spatial super resolution means like taking coarse geographic data and estimating it at a finer granularity. So for example, yeah, using county level data, like I have data that is divided by county, or I don't know, here in Brazil for states, and then trying to estimate it to the postal code level, or like to the city level or the neighborhood level. Which can be quite useful as well. So the final one is forecasting, like temporal forecasting. So they try to predict future values given a time series for each location. So for example, they tested on the unemployment rates, like they had the unemployment rates until 2022, and they tested on forecasting it to 2023 for the same location. But in this case, they had to use another, like a specific time forecast model in conjunction with the PDFM. So yeah, for each specific task, the researchers they took the embeddings and used them as features in a simple supervised model. They tried linear regression or small, like neural networks. And then they evaluated them. So here in like the GIF that's shown below, one of like the super resolution tasks that they used was they started with the county data on median household income in the state of New York, and then they tried to make it more granular, right, like to the counties given the embeddings. And I think the GIF kind of shows actually like the real. Let me wait. Yeah, later they compare it to the real data of the postal codes, the zip codes, and it performs really well. So yeah, like about how they evaluated the test. So they compiled like 29 different variables, so health, socioeconomic, and environmental. So health can be something like diabetes prevalence or obesity rates in a county or zip code. Economic, like median income or population density. Environmental would be like elevation or tree covers. And these are already like was already a structure set out by the benchmark that they had published previously to the model, and it's one of the benchmarks that is used in GeoFM research currently. So yeah, for each of those variables and for each task type, they train those very straightforward models using the PDFM embeddings, and by using like a fairly simple model, it's really about like trying to test how much how much the foundation model can really like generalize. And for example, if linear regression can do a good job, that means like that the embedding is explaining that location pretty well and it's representing it pretty well. So what they used to compare the other foundation models that they used were so SetClip, which uses satellite imagery for local representation, GeoClip, which is like a similar idea, but it's like with geotagged photos from the ground, like street map photos. And they also compared it against IDW, which is inverse distance weighting, which is a very classic GIS algorithm just to interpolate. So as metrics, they use R-square for the interpolation and extrapolation test. For super resolution, they use correlation coefficient, and yeah, these metrics will focus on how close the projections are to the actual values, right? So yeah, if the PDFM like embeddings are good, then it should the downstream model should outperform the baselines. Pretty simple logic here. But yeah, now comparing to those other three like baselines across the different tasks, yeah, we can see that the first one, I don't know if everyone can see, right? The first set of bars here is the interpolation. Second one is the extrapolation test. The third one, the super resolution task. And yeah, in almost all cases, the population dynamics FM performed better. Even for extrapolation, which is a more challenging kind of task. The exceptions were that purely geographic variables, like, for example, elevation, or environmental related variables like tree cover, they were like elevation, for example, the IDW did better, which is the simpler method, but it's because elevation, it makes sense, right? Because elevation changes smoothly and like deterministically with distance, right? So the simple like distance weighted average does already quite well. And like the environmental, like tree cover, the satellite image based ones tend to do a little bit better as well, because they're already kind of focused on satellite imagery. But yeah, it's still like we can see that across tasks, the population dynamics one seems to perform very, very well. Even in tasks that wasn't supposed to be like the strongest for. And that it kind of validates that foundation model kind of approach, right? That combining multiple signals can create like a strong representation of that location, even outperforming very specialized approaches. So also about the fourth task, which was the forecasting one, just like given a general outline that they use like a times FM, which is, I believe is also like a Google model, like for time like forecasting, and they used it in conjunction with the PDFM embeddings to try to predict. In this example here, it's poverty. So what they did was they had like a historical time series for poverty aggregated by month, and they let the times FM model make a prediction for the next time step for each location, and then they took the PDFM embedding for that location and put both the embedding and the times FM forecast into a simple two-layer neural net to produce like a final adjusted prediction. So yeah, the thing is that with times FM, it will be the model that will capture the temporal patterns, but it doesn't know anything about like the neighboring relations. And then the PDFM will come with this information and the information about the population in there. So actually the results were quite good when they were used in an aggregated way. You can see it in the last row here. So yeah, it outperformed the fully supervised traditional model and the times FM by itself. And what's really interesting is that the PDFM embeddings, they're static. They're not going to change over time, right? They're like a snapshot. But yet, when used in conjunction with the forecasting, like in a neural network setting, they still enhance those forecasts. And this suggests that knowing the fixed or like more static attributes of a place, its socioeconomic things in the population behavior, can help predict how a metric evolves. So, for example, two counties, they might both have like rise in unemployment last year, but if one of them is a more like economic resilient kind of location, I don't know, like with high education or more diverse industries, and the other one is more vulnerable, then the same trend might not continue equally in both. So that's something that like the location awareness can really bring into like those kinds of temporal task. But still, it's kind of like a weakness still, or something to improve in the research here, because like the models are kind of complementing each other, but it's not like a foundation model that is already like bringing into the temporal layer into play here. They just use it as an example of something that can be done like on the side. So yeah, comparing it to other GeoFMs in general. So we've seen like setclip against setclip, which is essentially like a visual model for geography, like based on satellite imagery. It's really a good model when it comes to capturing like the physical geography of a place, like the vegetation or the construction density. However, it may not know things like the income level of the population there, or the health trends in this case of the population. So the PDFM, by incorporating both the human-centric data and the environmental signals, yeah, that's probably why, like here in this discussion, it performed better. And also, yeah, they're quite different in architecture as well. Just to point out, the setclip, it's I think it's like a transformer on images, and the PDFM is a GNN. So and against like the geoclip, like why maybe perform better. So geoclip, it uses like the street maps kind of images, and you can tell how a place looks from the street, right? Like you can see some signals indicating like wealth, if you see like a fancy house, or if it's like a torn down structure, it might seem like a poor or more vulnerable place, or you can see if it's greener or if it's polluted or not. But once again, like the satellite image is just one modality, and PDFM has like a kind of a multimodal approach in that sense. And it's still like it has the relationships into play, right, with the graph structure. And there are other models like SAT-MAE, which is a masked autoencoder on satellite images, and that were not like explicitly tested. But yeah, it's something that they could that I'll be interested to see, like how it relates to other, like for example, like the text based foundation models as well. Like they only chose a few of the models at the time to compare against. And yeah, they didn't at the time try to compare it against another knowledge graph based model, which would be interesting to see that they did it. So one other thing that was nice is that also they tried to use setclip features, which is the satellite image foundation model, into PDFM as another input, and it also improved PDFM's performance. So I think this is cool for us to think about maybe when trying to experiment with these geo foundation models, that we can consider maybe thinking more broadly about what data to include, and like a more mixed approach is proven to be better. Trying to use like mixed frameworks and mixed data sources instead of very specialized ones. Just talking about the population dynamics model strengths and limitations. So what it's really good at, first, the multi-model integration, so like the data fusion, right? So it's, as I've been saying, like I think that's its biggest strength, like how it fuses multiple data modalities and data types, whereas like most models just stick to one type of data. It throws in everything, even from internet search to physical environmental data like a tree cover. So the embeddings are quite rich and having like a little bit of everything. And yeah, we could see that they prove to be fairly powerful in predicting across like different tasks. Um, so yeah, that's another thing. So the general purpose, so the generality of it all, like how we could use these embeddings for like different sets of tasks, and instead of usually geospatial like tasks, they're very task specific, like the data sets and how we interpolate things and how we aggregate things. So this can be quite powerful in that sense. Like minimizing like the fine tuning and having like a more general model that could apply to different tasks and predictions. So also a good thing is the graph reasoning, so like the relationship kind of understanding that we get from this structure. So it knows that locations are independent points, which is usually if we use like a traditional AI model, it will assume that about locations. And yeah, we can better understand that as like a connected fabric and the sense of distances. And it deals better with like irregularities, like for example, like different areas, like different sizes or missing data points, better than like a image-based, for example, like method would be able to. And as I've been saying, it's also fairly interpretable because they have that like disentangled embedding structure that we can kind of divide the vector by like the themes. So we can better interpret results. And it's also like extensible, so kind of like a modular kind of design, more flexible, like we can put in additional signals, like as I just mentioned, the set click features, for example, to further improve it with understanding that is more like through the raster layer level. And a good thing is also like that it's, for now at least, it's fairly accessible. I wouldn't say it's completely open source, but yeah, Google released like the notebooks and embeddings so that people can experiment with them. Google has also recently released like a satellite focused satellite image and sensor focused foundation model, which is called Alpha Earth, but for the entire globe, which could be something to look forward to in try to associate both, like for their strengths, like the human side of it and the more environmental side of things. But also it comes with limitations. So as I mentioned, there's that kind of thing like that the embeddings, like they're static. So they're like snapshots of that place at that time. And the temporal kind of prediction effort that they have here is more of like a thing to try to get two models together in a neural network to, instead of just applying the temporal layer to the generalization of the foundation model itself. So yeah, I think that's like something that future work could improve on. So yeah, like there is also the thing about the like some kind of data time misalignment, I would say, because the inputs they come from different time periods. So it's some kind of mismatch, and this comes a lot with like public data. Like there's often like a mismatch in that kind of in the temporality of the data that can introduce some noise. Like for example, like the model might link search trends from 1 year with map data, like the land cover from 2 years later. And maybe that can be fine, but if there's like something big like changed in between, for example, like a new highway was built 1 year ago, like the model wouldn't know that from that data. So yeah, that is a challenge, but I think that's a challenge in like geospatial things in general as well. And also, like of course, like this this model was trained and built for like very United States centric, I would say, because they use like the zip codes and the counties, the American ones. So yeah, we don't know like how it would perform in other regions, right? In yeah, global south or more like rural areas with less data. Um, so that's kind of a challenge, and of course, like I know that they had to do that because like trying to map out the different data sources across like different countries, like the human-based socioeconomic thing side of things would be very difficult. Um, not the same like they released the Alpha Earth thing, like it's global because it's satellite image based, so uh, that's a little bit more attainable, but not when you try to get like sensitivity data or demographic data or even like the Google search data into it. So yeah, like it also there's also like the input data gaps. Like it combines many data sets, but not doesn't include like everything. It doesn't include other economic indicators that I think would be nice, like GDP, crime statistics. But that is something like that I understand can be improved on, of course, and it depends on they had the target here for like health applications, and just the benchmark, like the ground truth itself, it can be noisy in the sense like some of the health stats that they use in the paper, like they're already estimates. So they're kind of evaluating on estimates itself. So that's something that I would also keep in mind. And yeah, finally, limitation is the complexity. It's a very large model. Training it takes a lot takes up a lot of resources. I know we're day by day overcoming that, or in the past to overcome that. But yeah, it makes it untrivial to kind of like update it very frequently. So yeah, which is like typical foundation models, like, being expensive to build, and uh, so but yeah, if we were to attempt to do something like that, it's not exactly trivial, right? Um, but still, as just like final takeaways, I think uh, like the geospatial foundation models, they can be like very very transformative, very interesting to do with, because we could have more generalized models like to apply to different tasks, and handling many tasks with one model reduce a lot of the current efforts to try to over like specialize some things, which takes up a lot of resources. Uh, so yeah, it also has the potential. Uh, it shows the potential of like embeddings as like a fingerprint of those locations, like how geospatial embeddings can be applied to many contexts, which I think for us like could be nice to apply to credit risk, marketing, like different types of applications. Um, so finally, also like it's adaptable and flexible. We can use it in conjunction with other models. Keep keep trying to add new signals, new data, and test it out with different pipelines. And yeah, I think it's just like the final takeaway would be to it's a field that is like moving very very fast, and I see a lot of different companies big companies trying to come out with their biggest and better foundation model right now. So yeah, I think it's just something for us to keep in mind, and hopefully experiment in the near future soon. Um, and yeah, I think. Oh, I just repeated this slide. Sorry. Um, but yeah, here it's just some extra resources. I'm going to share the slides in the paper club thread. yeah, just the paper itself. They have like a blog post that kind of summarizes the results as well. GitHub with like example notebooks, and I also have the paper as like a more general overview of geo foundation models if anyone wants to check it out. Yeah, that would be all. Thank you, guys.
Thanks, Stéfany, for the presentation. I think this is really interesting, right? This idea of a foundational model for geospatial things. I think this could be something that we could try to leverage this information, right, for any aspect that we have, right, from our data, and how, especially how to find uh, places or situations that are similar, right, in different points of time or space. Stéfany, I have a question for you. Like, first, like, what is your opinion? Like, do you have anything to say about like this work uses a lot of graphs, right? GNNs, and you have like you know a lot about the traditional models, right? TWR, etc. I would like to know your opinion on like the use of GNNs, like how they are able to integrate different types of data, and this part of like message passing, right? So it has a node pass to the neighbors and things like that. Like, what do you think of this approach?
Yeah, like I think it's because what I tend to experiment with is like the more classic like geospatial data science side of things. Oh, sorry, I can see you guys' oh, it's just hands up, right? Feel
Yes.
free to interrupt me, by the way. But um, which is more the traditional way of trying to interpret relationships, which is through distance and through like contiguity, like what polygon kind of touches the other polygon, right? And the neighboring like rings. So I think like it's very powerful to try to have like a more graph-based understanding of those relationships of neighboring, and like I really like the edge that they make with the human behavior, kind of interesting, like similar human behavior, making the places more similar to each other, closer to each other, right? Uh, which I think is something that I personally had never seen like in more traditional like geospatial data science or econometrics kind of studies. Um, so yeah, I think it's one of the things that might make this. Of course, like I'm not very well versed, but I think it's one of the things that might make this type of model like fairly powerful. Is that graph-based kind of structure as well, which I think is really cool.
Nice. Henrique?
Yeah, pretty cool presentation. We are seeing this explosion of foundation models for everything. Geospatial seems a really good idea. I have two questions actually. Do you think foundation models are possible in the sense of not only like looking into as if it was a map, like trying to find out poverty rates in some kind of map? The same foundation model would be able to solve that and how to move a robot, something like that. And how close, the second question is, how close are we to an actual foundation model, geospatial foundation model?
Yeah, no, I my hope would be that we would be able to use for all those kinds of tasks, you know, like anything that has to have like spatial awareness. I that is like the goal, right? It's something that can be generalized in that point, I believe. But I think there's quite a lot of work to do because, for example, I think this is only like the first, like I think set clip, for example, was released in early 2024. But I think it's like it's fast growing. I can't. I always am a little bit wary of like making predictions like that, like oh when we're gonna reach that. But I think we're not too far away. I think like the foundation models kind of like field in general as well, like is super quite fast paced, fast growing. I think like the geospatial side of things tends to like lag behind a little bit. But at least like I see like on LinkedIn, I follow a lot of people that work on these things, and they're always very excited and publishing things. So I don't know. Maybe I think like in 1 year, like 1 to 2 years, like we have something like super powerful. It's cool to.
The GPT moment.
Yeah, I hope I would like that. I saw like a cool like effort of like a researcher that he tried to make GPT understand like space through strings, which is like a different way of organizing, because we have like the WKT representation for like a polygon. So it's like polygon and then parentheses and like the coordinates inside. And then he would tweak like the string in a way that would try to make like GPT better understand the polygons, and would try to make like relations like, oh, what is neighbor of what, like what is like, is this square inside that other square, because that seems like a fairly simple thing, but GPT can't do that at all. And he actually had interesting results with that. Like it was crazy, like the way he manipulated the strings, but it made GPT understand it better. So that's also interesting. Like I would like to see more advances regarding that, like a mixed kind of geospatial like language hybrid kind of foundation model too. That would be nice.
Rodrigo?
Stéfany, great one. Really interesting work and super nice presentation. I think that we need a blog post about it. I can write and then with you in a collaborative way. I think this is super nice, like for real. And two things that I was thinking during the presentation is I would love to see how this model performs under uncertainty or under missing data in a sense, because we don't have data for, I mean, in this specific case, maybe we have data for all the US, but maybe we want to get this model transferred to other regions where we don't have like the full scenario. And it would be amazing to see how this model performs under uncertainty for those downstream tasks. That would be really nice to see. But I think that's just an observation. The second thing is, I didn't know that people were building such cool foundation models using GNNs, especially like a simple GNN, because this is Sage Graph, right? So it's basically message passing. There's no like anything more complex than graph convolutions and stuff. And I know there is like this idea of a spatial temporal GNNs, where they basically break the GNNs into graph convolutions, which are spatial, aggregate information from neighbors, but that's just what they do. And there is also this idea that you can do temporal convolutions. So you basically aggregate information from the neighbors, and then you do a temporal convolution, and you can have time series for each node as a node feature. So this is like this super cool idea of how can we make time series data into this geometrical structure as graphs. So it's really cool to see those type of foundation models. But yeah, I think that was it. I didn't have like a specific question, just a bunch of thoughts. Sorry.
No, yeah, I think that's very interesting, and yeah, it's cool to know about those other like graph kind of structures to try to incorporate the temporal data, like, because I think that's one of the main like limitations right now. It's like more seamlessly incorporating like the spatial temporal relationship. So I'll definitely look into that. Thanks.